shall be discussing about frequency domain representation of discrete signals. Before we go to the frequency domain representation, we will just briefly discuss about how to represent a continuous domain dynamic system in a difference equation mode. Okay. Then we will take up frequency domain representation. Suppose you have a differential equation in the continuous domain, 2 into d square x by dt squared plus 3 into dx by dt plus 2 into x is some forcing function ft. Now, we have approximated dx by dt as some first order approximation of this kind, xn minus 1 by t, where t is the sampling time. Alright. That means, if there is a continuous function, if you want to evaluate at some interval this function is given, then the derivative is approximated as the difference between the two successive points and the slope. Okay. D square x by dt squared similarly will be xn minus twice xn minus 1 plus xn minus 2 by t squared. This we observed last time. So, this differential equation can be written as 2 into xn minus 2 xn minus 1 plus xn minus 2 by t squared plus 3 into xn minus 1 by t, 3 into dx by dt plus 2 into xn is equal to fn. Okay. All right. This you can simplify. Multiply by t squared, and it will appear finally in this form, sum a into xn plus b into xn minus 1 plus c into xn minus 2 is equal to sum fn. The right hand side could have been also given in a differential form, ft plus some constant times f dash t and so on. So, that would have generated fn, fn minus 1 and so on. Okay. So, this is the general form of differential equation. We can write in the general form some fn plus a d times fn minus 1 or fn minus 2 and so on. So, this is the difference equation form, that is in the discrete domain we write a dynamic system equation in this form. Now, we come to frequency domain representation. Before we go to the discrete domain, let us concentrate on the frequency response of systems in the continuous domain. You are given a transfer function Gs, you are having an input Ft, corresponding output is Yt. You convert Ft into Fs, Yt in the transform domain it becomes Ys. So, Fs, if you remember, is Fs times Gs is Ys in the Laplace domain, or in the frequency domain you have also studied the frequency response if Ft is say a sin omega t, a sinusoidal input. If you give a sinusoidal input, what will be the corresponding output? The output can be evaluated very easily, and under steady state condition it will be A, this is multiplied by a gain function which can be obtained by putting j omega, alright, and then sin omega t, there will be an additional phase which will be the angle associated with gj omega. If I substitute for s equal to j omega, then this will be gj omega magnitude and an angle phi. So, that phi gets added with this signal. So, this will be the response of the system yt. Okay. So, in the discrete domain, we would like to study if you are giving a discrete signal, discrete sinusoidal function, what will be the corresponding output. Let us see what it means. Suppose this is a sinusoidal function, you are sampling it at regular intervals of time t. Okay. So, t is equal to nt, all right. We can say we are exciting it by a complex sinusoid. I can always write this e to the power j omega t. What will be the corresponding discrete domain representation? E to the power j omega n t. Okay. So, that gives me e to the power j to n. This capital omega, henceforth we shall be representing the analog domain frequency as capital omega, that is radian per second, and omega into t is also a frequency, we call it radian frequency, we will represent by small omega. Okay. Henceforth, this small omega will be used to represent a discrete domain frequency which is only radians, all right, and this is in radians per second, which is 2 pi into the normal frequency in hertz. Okay. So, this will be e to the power j omega n, all right, e to the power j omega n. Now, we are exciting the signal by e to the power j omega n, that means a sinusoid which is discretized. So, what we are trying to see is, if I excite it by a signal of this kind, this is the kind of pulse that you are sending, all right. That is, its envelope is a sinusoid, but its discrete version is taken as a sequence, all right. You are exciting it by this kind of a signal, and this will give you an output which is also measured at regular intervals. Whatever is the output, you are measuring that output also at regular intervals. What will be the ratio of the magnitudes and what will be the change in phase? Okay. That will be depending on the system's behavior. So, the ratio of the magnitudes will give you g j omega something corresponding to similar to this function, all right, and the phase associated, that is you will find there is a phase shift. So, phase will be associated with again that function g j omega in the continuous domain. So, we shall be writing something like e to the power j omega, we will come to this very soon, and angle g e to the power j omega. In the discrete domain we do not write j omega, we write e to the power j omega because it appears in this form. Okay. It is a matter of convention. Now, you have observed, if I excite a system whose impulse response is Hn, if you excite it by Xn, the corresponding output is Xn convolution Hn. This we observed last time. Now, suppose Xn is e to the power j omega n. So, what will be the output? Convolved with Hn. Okay. And what was the convolution expression? If you remember, summation e to the power j. Okay. Let us excite it by e to the power minus j omega n. It will be just e to the power minus j omega n. So, minus j omega n minus k h k. Do you all agree? I can write e to the power summated over k. E to the power minus j omega n can be taken out, and I can write h k e to the power, all right, let us put it as plus itself, sorry, h k e to the power j minus omega k summated over k. Let us write plus j omega. So, now you see, if I excite the system by an exponential complex function like this, the response is the same function e to the power j omega n multiplied by this h k e to the power minus j omega k. For a given h k, this is a unique function, a frequency domain function. Okay. I call this as capital H e to the power j omega, all right. This represents the quantity here h k e to the power minus j omega k. This is known as frequency response of the system or discrete time Fourier transform of the system. In the discrete domain, in the time domain it is discrete. So, discrete time Fourier transform, it is a Fourier transform of the system, h n is converted to h e to the power j omega, all right. Now, what is the nature of this function? Let us see. It is very similar to e to the power j omega, h e to the power j omega is very similar to g j omega in the continuous domain. Okay. So, this is a complex quantity, this is also a complex quantity. Suppose I have for a system h n is given as h 0, H1, H2, H3 like this, 2 minus 1 plus 1 and 0.5. These are the values. What will be the frequency response? H e to the power j omega corresponding to this will be 2 plus e to the power minus j omega into minus 1 plus e to the power minus j 2 omega into plus 1 plus e to the power minus j 3 omega into 0.5. Okay. It is, see, H0 plus H1 e to the power minus j omega plus H2 e to the power minus j 2 omega plus H3 e to the power minus j 3 omega. Is it not? So, I have just used that. Okay. You can evaluate this for different values of omega. So, one may take omega equal to 0, 0.1 radian, 0.2 radian, 0.3 radian and so on. You can compute it. We can take, instead of such discrete values of 0.1, 0.2, you might as well take 0.1 pi, 0.2 pi, 0.3 pi, that would be very convenient. Then you can go to 2 pi, then 2.1 pi, 2.2 pi and so on. Okay. Substitute these values and then see how it changes. Now, this kind of a function is periodic. Can you see this? If I take a step of 2 pi, that is say omega equal to 0.1 pi, okay, what will be the value? H e to the power j 0.1 pi, it will be 2 plus, okay, minus 1 into e to the power minus j 0.1 pi plus 1 into e to the power minus j into 2 into 0.1 pi plus 0.5 into e to the power minus j 3 into 0.1 pi, okay, whatever be that value. And if I take 2.1 pi, that means after a jump of 2 pi, what will be the value? 2 plus minus 1 into e to the power minus j 2.1 pi plus all other terms. Now, what is 2.1 pi? E to the power minus j 2 pi and minus 1 pi. So, it will be 0.1 pi. E to the power minus j 2 pi minus j 4 pi, all will be equal to 1. So, from the second term and third term you will get e to the power minus j 4 pi, e to the power minus j 6 pi. So, finally, the same terms will be reappearing. So, it is having a periodicity of 2 pi. Okay. If you make a plot, therefore, suppose at 0, what will be the value of this function at omega equal to 0? Will be just 2. These will all be reducing to 1, sorry, e to the power 0 pi. So, e to the power 0 pi, how much is it? All it will be reducing to 1. So, it will be Is it all right? So, this will be 2 plus minus 1 plus 1 plus 0.5, whatever be that value, it will be coming here. At 0.1 you have measured the magnitude and phase. So, if I take the magnitude, now if you take minus omega, these signs will be just opposite. Okay. Your series was H0 plus H1 e to the power minus j omega plus H2 e to the power minus j2 omega and so on. So, for any value of omega, whatever imaginary part you get, for minus omega you get just the conjugate. Okay. So, the magnitude remains same, it is a phase which will be opposite, alright. So, magnitude will be for both positive and negative direction of omega, you will get the same magnitudes. So, it may be function like this, okay. But then it is symmetric. It will have a repetition after every 2 pi. On this side also, if you produce it backward, then it will be after minus 2 pi, minus 4 pi and so on. Okay. So, there is a period of 2 pi, the values will be lying here. So, 0.1 pi and 2.1 pi will be identical. Is it all right? The response of the system corresponding to 0.1 pi and 2.1 pi will be same. What is 2 pi? What is it in terms of absolute frequency? Suppose you are having a system where you are having a sampling time corresponding to a frequency of 2 kilohertz, means 0.05 second or 0.005, t is equal to 0.005 second, okay. That means 2 kilohertz. So, 1 kilohertz will correspond to half that sampling frequency, alright. So, omega, any omega into t, which will give you the corresponding frequency, say 100 hertz. If I consider 100 hertz, what will be its representation in the discrete frequency domain? It will be 100 multiplied by 0.005 radian, alright. So, 0.5 radian, alright. 2 kilohertz will correspond to is it all right? Point. So, 100 hertz, actually 100 hertz is 100 into 2 pi okay, so many radians per second, all right. So, its omega is corresponding to 628 radians per second. So, omega into t will correspond to 628 into 0.005. So, it is not 0.5 radian into 2 pi, so 6.28. So, that will be the radian. Okay. Similarly here, so this is 3 point or 0.314, 0.314 radian. Is that all right? No, 3.14 radian. Okay. 100 hertz will correspond to 3.14. It is 100, 1/10. It will be. You see, there is a 0 here. Or 1/2000 is 3 zeros. Is it all right? Okay. There was a slip. So this will be equal to 0.314 radian. All right. So what I meant is, in terms of the sampling frequency corresponds to 2 pi. In the radian domain, sampling frequency will correspond to 2 pi, is it not? Because omega s into t is 2 pi into fs into t, and fs into t is 1. So that gives me 2 pi radians. Okay. So any fraction of that will be that fraction of 2 pi. So 100 hertz was 1/20th of 2 kilohertz. So 1/20th of 2 pi. So 100 hertz therefore, and 2 kilohertz plus 100 hertz, that is 2100 hertz, will appear identical. The response of the system corresponding to 100 hertz and 2100 hertz will be identical. Is it not? That is what we have observed. 1.1 pi and 2.1 pi. 0.1 pi corresponds to, say, 1/10, 0.1 pi may be corresponding to some frequency like 100 hertz, say, and this will be 2.1. That means at a gap of that sampling frequency, 2 pi corresponds to sampling frequency, you get the identical response. So 100 hertz and 2100 hertz will give me the same response when the sampling frequency is 2 kilohertz. So if you change the sampling frequency, then only you can distinguish the response corresponding to these two different frequencies, not otherwise. Number one. Number two, if I change the sampling frequency, then the response due to these two will not be same. Okay. So sampling frequency is very important. So any omega and 2 pi plus omega, 4 pi plus omega will have identical response. Physically, what it means? Let us see. Let us have a sinusoid . I am taking just a cosine function. So varying slowly. these are the sampled points. Okay. I am also having another sinusoid like this. Okay. Now, I am sampling at this rate. See, the sampling rate is relatively slow, means the time gap is sufficiently high, sampling time is quite high. You have scanned these values from this signal. Somebody else has got another signal, he has scanned at the same rate, but they also fall on this line. Now, which particular signal from these values, these discrete values, which particular signal can you identify? There is an ambiguity. I could have had many more such signals, which will have these as the sampled points. I have not drawn it for many other frequencies, it is a little difficult to draw it here, and I could have shown you many more signals can be represented by the same discrete values. Okay. So, there is an ambiguity. So, what should be the, suppose the signal is having, it is like this, is having a lot of kinks here and there, that means a number of frequencies are involved, and what should be proper sampling rate, so that we can trap all possible frequencies. So, the highest frequency that is present here will have like this, say you take the maximum number of variations in that signal, that means where that high frequency component appears, and then sample it there. Okay. Let us see what it means. Any function I sample 2 points, these are the 2 values. If I just, or okay, let us take these 2 values. From this point to this point, the function has gone this way, it could have gone this way also. So, I could have represented with the help of these 2 sampled points, I could have represented an analog function, a continuous domain function, which has a part like this, that is also possible. So, there is a path like this, either a convex or a concave form. If you want to determine, if between 2 successive points there should not be any ambiguity, then it should not go through a maxima without having another sampling. If I would have had another sampling here, then I could have determined it has gone this way and not this way, another sample point should have been there. That means between, say, on the 2 sides of a maxima or a minima, I should have sampling. Okay. That means if between 2 points there is a maxima or a minima, then I must have another sampling there. Okay. Let us consider this. If I sample it here and here, both may mean 0, it could have been this way or this way. This is half the frequency present. So, I must have at least a sampler which will sample values in between. So, if I can sample somewhere here, then I know it is going this way, it cannot be this way. Okay. This is half the frequency. So, I must have a rate faster than half that frequency, this is corresponding to this is twice the sampling frequency. See, if I sample at this rate, sampling frequency is twice this frequency, okay. So, it must be more than twice that frequency, okay. Physically it means this, if I can have a sampler whose sampling rate, you are sampling at this rate which is twice the frequency of the signal, this is the highest possible frequency present, say. So, if I want to trap that, then I must have a sampling frequency which is higher than twice that frequency, that is sampling time should be half of this, less than half of this. This will derive sometime later also mathematically. Let us consider for the time being, let us consider Laplace transform of a continuous domain. Hurriedly we shall go through the standard Laplace transforms, then we will go for discrete domain transform. What is the Laplace transform of a function f t which is say e to the power minus a t. So, we know this is 1 by s plus a, okay. So, if I put a equal to alpha plus j beta, then Laplace transform of e to the power minus alpha t, okay, e to the power j beta t will be 1 by s plus alpha plus j beta, okay, which is s plus alpha minus j beta by s plus alpha whole squared plus beta squared. If we segregate the real and imaginary part, then the real part of this will be e to the power minus alpha t cosine beta t. So, Laplace transform of this will be real part of this, which is s plus alpha by s plus alpha whole squared plus beta squared. Why I am doing this is this, that by the same logic we shall be deriving the z transform of different time domain functions, discrete time domain functions. We need not go through the entire derivation. Similarly, if I take the imaginary part, e to the power minus alpha t sin beta t will be beta divided by, from both sides minus beta t minus j will get cancelled. So, it will be beta by s plus alpha whole squared plus beta squared. If you differentiate, once again e to the power minus a t, if you differentiate with respect to a is a common quantity, common variable. So, if I differentiate with respect to a, I will get t into e to the power minus a t, and that gives me on this side 1 by s plus a whole squared. Again the negative sign will get cancelled. You differentiate once again, t square into e to the power minus a t will give you 2 by s plus a to the power 3, and successively if you keep on differentiating with respect to a, you will get factorial n by s plus a to the power n plus 1. Okay. If you put a equal to alpha equal to 0, you get the Laplace transform for a pure sinusoid sin beta and cosine beta. We will be making use of this relation very soon. Now we come to discrete domain transform known as Z transform. We define Z transform of a sequence xn as, see, transform will be shown like this: capital Z of the function xn or the sequence xn is equal to x0, where I write x0 as nothing but x at 0. In many books they write x at 0 also, it is one and the same thing. Wherever it ends, okay. K may tend to infinity. If it is an infinite sequence, then it may tend to infinity, it may be a finite sequence also. Okay. So, let us see what will be the Z transform of a delta function. It is 1, then 0, 0, the sequence is like this, is not. A delta function is existing only at n is equal to 0, after that it is all 0. So, what will be the Z transform of this sequence? It will be 1 plus 0 into z to the power minus 1 plus 0 into z to the power minus 2 and so on, which is 1. What is the Laplace transform of a delta function? That is also 1. So, for a delta function both in Laplace domain and Z domain, the transformed function is 1. What is the Z transform of a delayed impulse, say delayed by 2 steps, 2 intervals? So, it will be 0, 0, 1, 0, 0, this kind of a sequence. Okay. So, what will be the Z transform of this? 0 plus 0 plus 1 into z to the power minus 2, is it not? So, it is z to the power minus 2. So, if there is a delay of 2 steps, 1 gets multiplied by z to the power minus 2. Okay. Any xn, okay, any xn if I shift by some n steps, it will look like 0, 0, 0, after n steps only it will appear, is it not? So, what will be the corresponding Z transform? So, 0 plus 0 plus 0, then starts with x0 into z to the power minus n plus x1 into z to the power minus n plus 1 bracket and so on. So, z to the power minus n can be taken common, it will be x0 plus x1 z to the power minus 1 and so on, which is nothing but xz. Okay. So, xz gets multiplied by z to the power minus n if there is a shift of n steps. In the Laplace domain, if you remember, if ft gives you fs, then ft minus tau was represented by fs, it was getting multiplied by s tau, e to the minus s tau. So, similar to this, here it gets multiplied by z to the minus n if the function gets shifted by n steps. Let us now consider a unit step. What will be the z transform of a unit step? Unit step is given by 1 1 1. Okay. So, what will be the z transform? So, u z, I write u z is 1 plus z to the minus 1, z to the minus 2 and so on up to infinity, and this is a GP series 1 by 1 minus z to the power minus 1. Okay. What will be an exponential sequence c to the power n? C to the power n is basically c to the power 0 is 1, c, c squared, c cubed and so on, alright. Suppose c is less than 1 and so on. Then what will be the z transform? 1 plus c z inverse plus c square z to the power minus 2 and so on, and this is again c z inverse is a common ratio. So, this is again a GP series which can be written as where this quantity must be less than 1, c z inverse must be less than 1, then only you can represent this. This means z should be greater than, okay. Suppose you are having a sequence, a function 1 minus 0.8 z to the power minus 1. So, c is corresponding to 0.8. Okay. What will be the corresponding inverse transform? Inverse transform, like Laplace transform, we just take the table and then see the values of the corresponding inverses. So, corresponding to 1 minus c z inverse, 1 by 1 minus c z inverse, I know the sequence is c to the power n. So, c is 0.8. So, it will be 1, 0.8, 0.64 and so on. Okay. This is the sequence. If I have 1 by 1 plus 0.8 z inverse, then c is minus 0.8. So, it will be 1 minus 0.8 plus 0.64 and so on. So, it will be like this, 1 minus 0.8 plus 0.64. It is progressively decreasing, but it is alternating in sign. Okay. What will be z to the power minus 2 by 1 plus 0.8 z to the power minus 1? What will be the corresponding time domain representation? So, z to the power minus 2, we have observed if a function is delayed by n steps, then the original function gets multiplied by z to the power minus n. So, we know the inverse corresponding to 1 by 1 plus 0.8 z inverse, this one. So, the whole thing gets shifted by 2 steps. So, it will be 0, 0, then 1, then minus 0.8, then 0.64 and so on. It is a sequence of this type. Okay. So, if I multiply by z to the power minus 2, the sequence is of this type. Now, let us come to another interesting function. What will be? Okay. What will be the inverse of 1 plus z to the power minus 1? It is minus 1 to the power n. So, it will be 1 minus 1, 1 minus 1, 1 minus 1 and so on. Okay. What will be 1 plus z to the power minus 2, 1 plus z to the power minus 2. Now, look at it. Look at it this way, z to the power minus 1 corresponds to 1 delay. If I had 2 delays, then that corresponds to z to the power minus 2, alright. So, I will get the same sequence with 2 delays. So, this is 1 minus 1, 1 minus 1 and so on. In between there will be only zeros, alright. I do not have anything like z to the power minus 1. So, in between I will just put some zeros. Okay. Now, you tell me z to the power minus 1 by 1 plus z to the power 3 minus 3. What will be the z inverse of this? Shifted sequence. So, it starts from here. So, it will be 1, then it will be 2 zeros minus 1, 2 zeros plus 1, 2 zeros minus 1 and so on. Okay. So, in the next class we will stop here today.